We'll start in 1 minute. Today we'll cover section 9.2 on the sum and difference identities, and then we'll get started in section 9.3 on the double angle, half angle, and reduction formulas. We'll begin with the cosine sum formula. If you have the cosine of alpha plus beta, that is equal to cosine of alpha times cosine of beta minus sine of alpha times sine of beta. And then the cosine difference formula, if you have cosine of alpha minus beta, that's equal to cosine of alpha times cosine of beta plus sine of alpha times sine of beta. Knowing these two formulas will be important. To demonstrate how to use those, let's evaluate cosine of 2 pi over 3. We know a way already to evaluate cosine of 2 pi over 3 directly. 2 pi over 3 is in the second quadrant, and the reference angle is pi over 3. And in the second quadrant, cosine is negative. So the value of cosine of 2 pi over 3 is the negative of the cosine of pi over 3, or negative 1/2. But I'm going to use this as an example to demonstrate the cosine sum formula. We'll rewrite cosine of 2 pi over 3 as cosine of pi over 3 plus pi over 3. And then we'll write cosine of pi over 3 times cosine of pi over 3 minus sine of pi over 3 times sine of pi over 3. Cosine of pi over 3 is 1/2. And we multiply that by cosine of pi over 3 again. So 1/2 times 1/2. And then minus, we know that sine of pi over 3 is the square root of 3 over 2. And then multiplied by the sine of pi over 3 again, square root of 3 over 2. And we get 1/4. 1/2 times 1/2 is 1/4. And the square root of 3 over 2 times the square root of 3 over 2 is 3/4. And 1/4 minus 3/4 is equal to negative 1/2, which we already knew. But for the sake of an example, that will be good enough. Cosine of pi over 12, this one's not as obvious. Pi over 12 is not a special angle, but if you think of cosine of pi over 12 as cosine of 4 pi over 12 minus 3 pi over 12, and then simplify those, this is cosine of pi over 3. 4 pi over 12 is just pi over 3. And 3 pi over 12 is pi over 4. And we recognize pi over 3 and pi over 4 as special angles. So this time we're using the cosine difference formula. So this will be cosine of pi over 3 times cosine of pi over 4. And then we're going to add the sine of pi over 3 times the sine of pi over 4. And we know the values of all of those. Cosine of pi over 3 is 1/2. Cosine of pi over 4 is the square root of 2 over 2. And then we're adding that to the sine of pi over 3, which is the square root of 3 over 2. And the sine of pi over 4 is the square root of 2 over 2. So we'll take it a little bit further. 1/2 times the square root of 2 over 2 is the square root of 2 over 4. And we're adding that to the square root of 3 over 2 times the square root of 2 over 2. And that's the square root of 6 over 4. We can simplify this further, but I'm sort of out of room, but you'll get the idea. Okay, the sine function has a sum formula also. The sine of alpha plus beta is equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. And the sine difference formula, sine of alpha minus beta, is equal to sine of alpha times cosine of beta minus cosine of alpha times sine of beta. So we'll demonstrate the sine sum formula by evaluating the sine of 7 pi over 12. Uh, 7 pi over 12 is 4 pi over 12 plus 3 pi over 12. 4 pi over 12 is just pi over 3. And 3 pi over 12 is pi over 4. So using the sine sum formula, this is equal to the sine of pi over 3 times the cosine of pi over 4, and then plus the cosine of pi over 3 times the sine of pi over 4. And we've learned how to evaluate each of those. So I'll squeeze that in a little bit. The sine of pi over 3 is the square root of 3 over 2. Cosine of pi over 4 is the square root of 2 over 2. And then we're adding that to cosine of pi over 3, which is 1/2. And then sine of pi over 4 is the square root of 2 over 2. So let's simplify it a little bit more. Square root of 3 over 2 times the square root of 2 over 2 is the square root of 6 over 4. And then plus 1/2 times the square root of 2 over 2 is the square root of 2 over 4. This could be simplified a little bit more. Okay, on this one, sine of pi over 12. Well, we saw earlier that pi over 12 is just pi over 3 minus pi over 4. So I'll just rewrite this as sine of pi over 3 minus pi over 4. And this time we're going to use the sine difference formula, sine of alpha minus beta. So this is equal to sine of pi over 3 times cosine of pi over 4 and then minus cosine of pi over 3 times sine of pi over 4. Okay, and once again, we know all of those values. The sine of pi over 3 is the square root of 3 over 2. We multiply that by the cosine of pi over 4, which is the square root of 2 over 2. And then we subtract. Cosine of pi over 3 is 1/2, and the sine of pi over 4 is the square root of 2 over 2. So we can squeeze in a more simplified version. The square root of 3 over 2 times the square root of 2 over 2 is the square root of 6 over 4. And from that, we subtract 1/2 times the square root of 2 over 2, which is minus the square root of 2 over 2. Okay, we're going to derive the tangent sum formula by using the fact that tangent is sine over cosine, and the sum formulas for sine and cosine. So I'm going to draw a border here. So first, write tangent of alpha plus beta as sine of alpha plus beta over cosine of alpha plus beta. And then in the next line, in the numerator, we'll just write down what sine of alpha plus beta is. That is sine of alpha times cosine of beta plus cosine of alpha times sine of beta. That's the numerator. And then in the denominator, cosine of alpha plus beta. That's cosine of alpha times cosine of beta minus sine of alpha times sine of beta. Okay, what we do next is probably not intuitive, but notice in the denominator on the left, we have cosine of alpha times cosine of beta. So we're going to multiply this expression by 1 in the form 1 divided by cosine of alpha times cosine of beta in the numerator, and then also in the denominator, we're going to multiply this denominator by the same quantity, 1 over cosine of alpha times cosine of beta. We're just multiplying by 1. There's nothing wrong with that. Multiplying by 1 doesn't change the value. It'll just change the appearance. Okay, so when we multiply this numerator by 1 over cosine of alpha, cosine of beta, we'll get sine of alpha times cosine of beta over cosine of alpha times cosine of beta. Then multiply the next term here by 1 over cosine alpha, cosine beta, and we get cosine alpha times sine of beta over cosine of alpha times cosine of beta. And then the same in the denominator. Multiply cosine of alpha times cosine of beta by 1 over cosine of alpha times cosine of beta. We get cosine of alpha times cosine of beta over cosine of alpha times cosine of beta. and then minus sine of alpha times sine of beta over cosine of alpha times cosine of beta. You can see that there's going to be a number of things that cancel. So starting in the upper left, cosine of beta divided by cosine of beta, that equals 1. So those are eliminated. In the next term in the numerator, cosine of alpha divided by cosine of alpha equals 1. In the denominator, cosine of alpha times cosine of beta divided by cosine of alpha times cosine of beta, this reduces to a factor of 1. So remember, the factor 1 stays behind. And then in the lower right, well, we don't get any cancellations, but that's okay. Now we can write down the simplified form. In the upper left part of the numerator, sine of alpha divided by cosine of alpha is equal to tangent of alpha. And then we're adding that to sine of beta over cosine of beta, but that's just tangent of beta. And then in the denominator, the lower left, we just have 1, and then minus sine of alpha divided by cosine of alpha is tangent of alpha, multiplied by sine of beta over cosine of beta, which is tangent of beta. Okay, so that's the tangent sum formula. This is what tangent of alpha plus beta is equal to. Tangent of alpha plus beta is tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. It's useful to know this identity. At the very least, you should know the sum and difference formulas for both cosine and sine. And if you remember those, you can always derive the sum formula for tangent if you have to by going through this process. The tangent difference formula, well, we would go about it. I'll just write down what the formula is after I mention a couple of things. To derive the tangent of alpha minus beta formula, you go through the same sort of process that we did above when deriving the tangent sum formula. But you can use the formula for the tangent sum to help you with the tangent difference. So tangent of alpha minus beta in the numerator is going to have tangent of alpha minus tangent of beta. And in the denominator, it's going to have 1 plus tangent of alpha times tangent of beta. So you can see how the two formulas are related. And while I'm on that subject, you can also note the similarities of the sine of alpha plus beta formula and the sine of alpha minus beta formula. So recognizing those similarities will help you memorize those. And the same is true for the cosine sum formula and the cosine difference formula. You can see the similarities in the two formulas. So work on memorizing cosine sum, cosine difference, sine of sum, sine of difference. And my advice is to also memorize the tangent sum formula and the tangent difference formula. But as I said, if you You can always derive those whenever you need them. Okay, we'll do a couple of examples where we demonstrate how to use the tangent sum formula and the tangent difference formula. So we'll start with evaluating the tangent of 7 pi over 12. We saw earlier that 7 pi over 12 is just pi over 3 plus pi over 4. So we can write this as the tangent of pi over 3 plus pi over 4. And then apply the tangent sum formula to that. So in the numerator, we get tangent of pi over 3 plus tangent of pi over 4, and then divided by 1 minus tangent of pi over 3 times tangent of pi over 4. Okay, so the angles are special angles. The tangent of pi over 3, well, you can think, well, that's sine of pi over 3 over cosine of pi over 3. Sine of pi over 3 is the square root of 3 over 2, and cosine of pi over 3 is 1/2. So you can think, if you momentarily forget, you can think through the process that tangent of pi over 3 is just the square root of 3. And then we add that to tangent of pi over 4. Tangent of pi over 4 is 1. And then in the denominator, 1 minus tangent of pi over 3 is the square root of 3. And times 1, so I won't write the times 1. But this is a perfectly fine answer for evaluating tangent of 7 pi over 12 using the tangent sum formula. Okay, the next one, tangent of pi over 12. We saw earlier that pi over 12 is just pi over 3 minus pi over 4. So to evaluate this, we have the tangent of pi over 3 minus pi over 4. Using the tangent difference formula in the numerator, tangent of pi over 3 minus tangent of pi over 4. And in the denominator, we have 1 plus tangent of pi over 3 times tangent of pi over 4. So we have the same angles, just different operators. Tangent of pi over 3 is the square root of 3 minus the tangent of pi over 4 is 1. So in the numerator, the square root of 3 minus 1. And in the denominator, we have 1 plus the square root of 3 times 1. So here's the answer for tangent of pi over 12. Okay, we'll verify two of the cofunction identities. So we've seen a couple of times that sine of theta is equal to cosine of pi over 2 minus theta. So we'll evaluate cosine of pi over 2 minus theta using the cosine difference formula. So cosine of pi over 2 minus theta is cosine of pi over 2 times cosine theta. and then we add sine of pi over 2 times sine of theta. That's applying the cosine difference formula. Well, cosine of pi over 2 is 0. So 0 times cosine theta. Sine of pi over 2 is 1. So we get 1 times sine of theta. And this is equal to sine of theta. So this verifies this cofunction identity. Okay, we'll do it in the other order. It's also true that cosine of theta is equal to sine of pi over 2 minus theta. So we'll use the sine difference formula, sine of pi over 2 minus theta. So this one we have sine of pi over 2 times cosine of theta, and then minus cosine of pi over 2 times sine of theta. Sine of pi over 2 is 1, so we have 1 times cosine theta. Cosine of pi over 2 is 0, so minus 0 times sine of theta. And sure enough, we get cosine of theta. Okay, in the next exercise, we will rewrite sine of x plus 11 pi over 6 in terms of sine of x and cosine of x. We'll apply the sum formula for sine of x plus 11 pi over 6. This is sine of x times cosine of 11 pi over 6, and then plus cosine of x times sine of 11 pi over 6. So what we have to do is evaluate cosine of 11 pi over 6 and sine of 11 pi over 6. If you want to draw the angle, so 11 pi over 6 is not quite 2 pi, it's pi over 6 short. So if you go counterclockwise and then stop 30 degrees short of 1 complete revolution, or pi over 6 radians. So this angle is 11 pi over 6. And the reference angle is pi over 6. Okay, so we know that this is the fourth quadrant. So in the fourth quadrant, sine is negative because the y-coordinates are negative, but cosine is positive. So we can write that cosine of 11 pi over 6, cosine is positive, so cosine of 11 pi over 6 is equal to cosine of pi over 6, which is the square root of 3 over 2. And sine of 11 pi over 6 has to be negative, so that's going to be the negative of sine of pi over 6, or negative 1/2. Okay, so we can substitute those numbers here, sine of x times cosine of 11 pi over 6, which is equal to the square root of 3 over 2, and then plus cosine of x times negative 1/2. This is an okay answer, but it might look nicer if you write it as the square root of 3 over 2 times sine of x, and then minus 1/2 cosine of x. That's good enough. Okay, now we'll do a similar exercise. Rewrite cosine of x minus 5 pi over 6 in terms of sine of x and cosine of x. We'll use the difference formula for cosine. So cosine of x minus 5 pi over 6 is cosine of x times cosine of 5 pi over 6, and then plus sine of x times sine of 5 pi over 6. We can evaluate cosine of 5 pi over 6 and sine of 5 pi over 6. 5 pi over 6 is in the second quadrant. It's not quite half of a revolution, so this is about 5 pi over 6. And the reference angle is pi over 6. And in the second quadrant, sine is positive and cosine is negative. So we'll write here that cosine of 5 pi over 6 is equal to negative cosine of pi over 6, or negative square root of 3 over 2. And then sine of 5 pi over 6 is positive sine of pi over 6, which is 1/2. So we'll substitute those values in. So we get cosine of x times negative square root of 3 over 2, and then plus sine of x times 1/2. So we can, this is okay for an answer, but we can write it as negative square root of 3 over 2 times cosine of x plus 1/2 times sine of x. Okay, in the next exercise, given that sine of A equals 4/5 and cosine of B is equal to 1/3, where both A and B are in the interval from 0 to pi over 2, find sine of A minus B and cosine of A plus B. Well, we have to do a couple of other things. Since we need to know cosine of A and sine of B, we might as well do that first. If sine of A, if this is our angle A, if the sine of A is 4/5, this right triangle works out pretty nicely because this adjacent side is just 3. This is one of those Pythagorean triples. And so we can tell that cosine of A is equal to 3/5. Cosine of A. So we need to know that. We also need to know what sine of B is. We're given that cosine of B is 1/3. So if you have an angle B and the cosine is 1/3, we need to find the opposite side, and that's not too hard to do. This is just going to be the square root of 8. Square root of 8, or 2 times the square root of 2. You can verify by the Pythagorean theorem. 3 squared equals the square root of 8 squared plus 1 squared. Okay, so sine of B is equal to 2 times the square root of 2 over 3. Okay, let's do the sine of a minus b first. Sine of a minus b is the sine of a times cosine of b minus cosine of a times sine of b. And we know all of those values. Sine of a is given to be 4/5, so 4/5 times cosine of b, which is also given to be 1/3. And we had to find cosine of a and sine of b. Cosine of a is 3/5 multiplied by sine of b, which is 2 times the square root of 2/3. So we can notice that the common denominator will be 15. So I'll write it as a single rational expression. And then this part of the numerator, 4 times 1, so we get 4. And then we're subtracting 3 times 2 times the square root of 2. So 4 minus 6 times the square root of 2. Okay, the next one, cosine of a plus b. Cosine of a plus b. This is cosine of a times cosine of b. Minus sine of a times sine of b. Cosine of a, we found that to be 3/5. Cosine of b is given to be 1/3. And then minus sine of a, that's given to be 4/5. And sine of b is 2 times the square root of 2/3. Okay, the common denominator is 15 again. I'll write that to the left since I have more space over here. So the denominator is 15, and the numerator, 3 times 1, and then minus 4 times 2 times the square root of 2, so minus 8 times the square root of 2. Okay, that's not so bad. So knowing the formulas, and then also knowing how to, if you're given that sine of an angle is something, you can find the cosine of that same angle and vice versa. Okay, we'll get started on the next section, 9.3. Okay, so we remember from section 9.2 that we just covered sine of alpha plus beta is equal to sine of alpha times cosine of beta plus cosine of alpha times sine of beta. And we also remember that cosine of alpha plus beta is cosine of alpha times cosine of beta minus sine of alpha times sine of beta. And we derived tangent of alpha plus beta using sine of alpha plus beta and cosine of alpha plus beta. The tangent of alpha plus beta is tangent of alpha plus tangent of beta divided by 1 minus tangent of alpha times tangent of beta. So we're going to derive some double angle formulas. Sine of theta plus theta, or sine of 2 theta. So we just use the sum formula for sine. Sine of theta plus theta is sine of theta times cosine of theta plus cosine of theta times sine of theta. But each of those is the same, just the factors are in different orders. So we can write this as 2 times the sine of theta cosine of theta. So the thing to remember here as an important identity is that the sine of 2 theta is equal to 2 times sine of theta times cosine of theta. Okay, we'll do a derivation of another double angle formula, cosine of theta plus theta, or cosine of 2 theta. So we just use the cosine sum formula. Cosine of theta plus theta is cosine of theta times cosine of theta minus sine of theta times sine of theta. But cosine of theta times cosine of theta is cosine of theta squared. And sine of theta times sine of theta is sine of theta squared. Okay, so cosine of 2 theta is equal to cosine of theta squared minus sine of theta squared. Okay, the next one, tangent of theta plus theta, or tangent of 2 theta. So we remember the sum formula for tangent. In the numerator, we have tangent of theta plus tangent of theta. And in the denominator, we have 1 minus tangent of theta times tangent of theta. But in the numerator, we simplify that to 2 times tangent of theta. And in the denominator, 1 minus tangent of theta squared. Okay, so the double angle formula, tangent of 2 theta is equal to 2 times tangent of theta divided by 1 minus tangent of theta squared. Okay, we have variations of cosine of 2 theta. The one that we derived above, cosine of 2 theta, is cosine of theta squared minus sine of theta squared. But remember that sine of theta squared is 1 minus cosine of theta squared. So we can replace sine of theta squared with 1 minus cosine of theta squared to get an equivalent identity, but just in a different form. So cosine of theta squared minus the quantity 1 minus cosine of theta squared. And then when we do the arithmetic, we get cosine of 2 theta equals 2 cosine of theta squared minus 1. This is what we get when we simplify this. So this is one of the variations. Okay, another variation. First, let's write down the first derivation. Cosine of 2 theta we found in the first place to be cosine of theta squared minus sine of theta squared. But this time, we remember that cosine of theta squared is equal to 1 minus sine of theta squared. So this time we replace cosine of theta squared with 1 minus sine of theta squared, and then we have another minus sine of theta squared. And then when we simplify, we get the other variation of cosine of 2 theta. Cosine of 2 theta is also, or can also be written as 1 minus 2 times sine of theta squared. Okay, we'll do some exercises using these double angle formulas. So let's just go over them quickly. So sine of 2 theta is 2 times sine of theta times cosine of theta. Cosine of 2 theta equals cosine of theta squared minus sine of theta squared. And we can find the other two variations by substitution. And then tangent of 2 theta is equal to 2 times tangent of theta divided by 1 minus tangent of theta squared. Okay, so let's apply those in a couple of exercises. Okay, this says find sine of 2x, cosine of 2x, and tangent of 2x. If tangent of x is equal to -8 and x is in the quadrant 4. So let's deal with that first. If tangent of x is -8 and in the 4th quadrant, so in the 4th quadrant, and so if we have something like this, if you construct a right triangle, this is our reference angle. The x is, this is what x is. So this side of the triangle is -8, or we could write it as -8, and this adjacent side we could write that as 1. So the tangent of that angle is opposite over adjacent, -8 over 1. And so the hypotenuse of the right triangle, well, it's the square root of 1 squared plus the number -8 squared. So the square root of 65 is the length of the hypotenuse. Okay, so sine of x, well, sine is negative in the 4th quadrant, so sine of x is equal to -8 over the square root of 65. And cosine of x, well, if x is in the 4th quadrant, cosine is positive. So cosine of x is 1 over the square root of 65. So we need to know those quantities in addition to the fact that tangent of x is negative 8. Okay, so let's begin with sine of 2x. Sine of 2x, if you forget the formula, you can write it as sine of x plus x, and hopefully you'll remember the sum formula for sine. But either way, sine of 2x is 2 times sine of x times cosine of x. So sine of 2x then is 2 times what sine of x is. Sine of x is negative 8 over the square root of 65. And we multiply that by cosine of x, which is 1 over the square root of 65. And we can do a little bit more arithmetic. Sine of 2x then is negative 16 over 65. Okay, now let's focus on cosine of 2x. Cosine of 2x, well, this is cosine of x squared minus sine of x squared. Cosine of x is 1 over the square root of 65. So we're going to square 1 over the square root of 65. And then from that, we subtract sine of x squared. So we're going to square the number negative 8 over the square root of 65. And then do the arithmetic. So 1 over the square root of 65 squared is 1 over 65. And then minus, when we square negative 8 over the square root of 65, we get 64 over 65. And so this becomes negative 63 over 65 for the cosine of 2x. Okay, now tangent of 2x. Okay, tangent of 2x. In the numerator, we get 2 times tangent of x. And in the denominator, we get 1 minus tangent of x squared. Okay, well, tangent of x is given to be negative 8. So in the numerator, 2 times negative 8. In the denominator, 1 minus the number negative 8 squared. So in the numerator, negative 16. And in the denominator, negative 63. But negative 16 divided by negative 63 is positive 16 over 63. Okay, we'll do a similar sort of exercise below. So on this one, we're given that 2 legs of a right triangle have lengths 5 and 12. So a possible subtlety here is that the 2 legs refer to the 2 sides of the right triangle that are not the hypotenuse. So the 2 legs are the 2 shortest sides. We know that the hypotenuse is longer than each of the 2 legs. And so the lengths of the 2 legs are 5 and 12, and theta is the measure of the smallest angle. So that means that the side whose length is 5 is the side opposite of theta, the smallest angle. So we can draw a right triangle. Theta is the smallest angle. 5 is the shortest side, so 5 has to be on the opposite side of theta. 12 is the length of the other leg. And if you apply the Pythagorean theorem, we can find the hypotenuse. So the hypotenuse squared is equal to 5 squared plus 12 squared, or 25 plus 144, which is 169. And the square root of 169 is 13, so the hypotenuse is 13. So we need to know, when using the double angle formulas, we're going to have to know what the sine of theta is, cosine of theta, and tangent of theta. So we can tell by looking at the right triangle, sine of theta is 5/13. Cosine of theta is 12/13. And tangent of theta is 5/12. Okay, now we're ready to evaluate sine of 2 theta. Sine of 2 theta, that's 2 times sine of theta times cosine of theta. So sine of theta is 5/13. So we have 2 times 5/13 times cosine of theta, which is 12/13. And do the arithmetic. In the numerator, 2 times 5 is 10. 10 times 12 is 120. And the denominator, 13 times 13 is 169. So sine of 2 theta is 120 over 169. Okay, cosine of 2 theta. The first variation will work just fine. So cosine of 2 theta is cosine of theta squared minus sine of theta squared. And cosine of theta is 12/13. So when we square that, square 12/13, and then we subtract sine of theta squared. So we get 144 over 169 minus 25 over 169. So cosine of 2 theta is equal to 119 over 169. Okay, finally, tangent of 2 theta. Tangent of 2 theta in the numerator is 2 times tangent of theta. And in the denominator, it's 1 minus tangent of theta squared. Okay, so tangent of theta is 5/12. So in the numerator, 2 times 5/12. In the denominator, 1 minus tangent of theta squared, so 1 minus 5/12 squared. So we're going to get in the numerator 10 over 12. In the denominator, 1 minus 25 over 144. So let's simplify a little bit. 10 over 12 is 5/6. We'll rewrite 1 as 144 over 144, and 144 over 144 minus 25 over 144 is 119 over 144. So just a little bit further, 5/6 times the reciprocal of 119 over 144. So 5/6 times 144 over 119. And 6 goes into 144. What, 24 times? So, yeah. So finally, 5 times 24 is 120, and the denominator is 119. So. Okay, we'll look at some identities to prove. I'm thinking that there's no end to how many identities can be thought up. So there's different approaches for proving identities. Ideally, the goal would, if you start on one side and continue working until you get to the other side, that's the ideal. Another method is to work on both sides simultaneously until the left-hand side is equal to the right-hand side. Oftentimes, it's easier to start with the more complicated side to see if you can simplify it to the less complicated side. So we might want to consider doing that in this case. The right-hand side looks to be more complicated than the left-hand side. So if we begin with the right-hand side and try to get it into the form sine of 2x, then that would be a valid approach. So I'll rewrite the right-hand side, 2 times tangent of x divided by 1 plus tangent of x squared. And then we'll rewrite each of the tangents in terms of sine and cosine. So in the numerator, we get 2 times sine of x divided by cosine of x. And in the denominator, 1 plus sine of x squared divided by cosine of x squared. So just like in algebra and arithmetic, writing expressions with a common denominator is usually something useful to do. So in the top numerator, I'll just write 2 times sine of x over cosine of x. And in the denominator, the least common denominator is cosine of x squared down here. So we're going to multiply 1 by cosine of x squared over cosine of x squared. So we get cosine of x squared plus sine of x squared all over cosine of x squared. And cosine of x squared plus sine of x squared is 1. So I'll write one more intermediate step, 2 times sine of x over cosine of x divided by 1 over cosine of x squared. And then another familiar maneuver whenever you divide a fraction by another fraction. It's equivalent to multiply the fraction on top by the reciprocal of the fraction on the bottom. So this is equal to 2 times sine of x over cosine of x multiplied by the reciprocal of 1 over cosine of x squared. So that's cosine of x squared over 1. And in this product, one factor of cosine is going to cancel from each. So we're going to get 2 times sine of x times cosine of x. And what do you know? 2 times sine of x times cosine of x, that's the identity for sine of 2x. Okay, so just to reiterate my earlier comments, we started on the right-hand side. Oh, I might as well write complete sentences. We started on the right-hand side and ended with the left-hand side. If you can read my writing. Okay, let's try another one. So, show that sine of 3x equals 3 times sine of x times cosine of x squared minus sine of x to the third power. Well, I think I'm going to start with the left-hand side this time, even though the right-hand side looks more complicated. We could start with the right-hand side, but I'm going to rewrite sine of 3x as sine of 2x plus x. And then I'm going to use the sum formula for sine. So the sine of 2x plus x is the sine of 2x times the cosine of x plus the cosine of 2x times the sine of x. And then I'm going to use the double angle formula for sine of 2x and the double angle formula for cosine of 2x. See what happens. So sine of 2x is 2 times sine of x times cosine of x. And so we multiply that by cosine of x. And cosine of 2x, one variation is cosine of x squared minus sine of x squared. I have to put that in parentheses to multiply that by sine of x. Okay, next, here on this part, when we multiply cosine of x times cosine of x, we get cosine of x squared. On the right-hand side, we'll distribute multiplication by sine of x. So we get cosine of x squared times sine of x, and then minus sine of x to the third power. Okay, we'll notice that this term, 2 times sine of x times cosine of x squared, is the same kind of term as cosine of x squared times sine of x. The factors are in different order, but those can be combined by adding, so we get a total of 3 times sine of x times cosine of x squared, and then minus sine of x to the third. So this is the right-hand side. So we completed the process and we showed that we proved the identity. So we started on the left-hand side and ended up with the right-hand side. Okay, the next page. We're going to derive some more formulas. We're going to derive what are called the reduction formulas. And we're going to begin with cosine of 2 theta. Okay, so we're going to use one of the variations of cosine of 2 theta to help us come up with a formula for sine of theta squared. If you're going to take calculus, knowing the reduction formulas will be very useful. Okay, so we're going to begin with cosine of 2 theta, which is cosine of theta plus theta. So this is cosine of theta squared minus sine of theta squared. But since we're trying to come up with a formula for sine of theta squared, we're going to replace cosine of theta squared with 1 minus sine of theta squared. So replace cosine of theta squared with 1 minus sine of theta squared. So we have cosine of 2 theta equals 1 minus 2 times sine of theta squared. So now what we want to do is solve this equation for sine of theta squared. That's what we're trying to do. Solve for sine of theta squared. Okay, so we can do a couple of things at once. We can add 2 times sine of theta squared to both sides and subtract cosine of 2 theta. So when we do that, we get 2 times sine of theta squared on the left-hand side, and on the right-hand side, 1 minus cosine of 2 theta. And then lastly, divide both sides by 2, or equivalently, multiply both sides by 1/2. So sine of theta squared is 1/2 times the quantity 1 minus cosine of 2 theta. This is referred to as a reduction formula because it reduces the exponent from 2 to 1. So sine of theta squared is equal to 1/2 times the quantity 1 minus cosine of 2 theta. So I'll make a note of that, of my comment. So the exponent, the largest exponent, is reduced from 2 to 1. Hence the term reduction formula. Okay, we'll come up with a reduction formula for cosine of theta squared. So once again, we begin with cosine of 2 theta. Cosine of 2 theta is cosine of theta squared minus sine of theta squared. And this time we're going to replace sine of theta squared with 1 minus cosine of theta squared. So this is cosine of theta squared minus the quantity 1 minus cosine of theta squared. I'll put in an extra arithmetic step here, cosine of theta squared. And so when we distribute subtraction, we're going to get minus 1. And in effect, we are subtracting negative cosine of theta squared, which is equivalent to adding cosine of theta squared. And so we get that cosine of 2 theta is equal to 2 times cosine of theta squared minus 1. So we're trying to come up with an expression for cosine of theta squared, so we're just going to solve this equation for cosine of theta squared. Okay, well that's not hard to do. We add 1 to both sides, so we get cosine of 2 theta plus 1 equals 2 times cosine of theta squared. And then divide both sides by 2, or multiply both sides by 1/2. Either way is okay. I'll write it as cosine of theta squared equals 1/2 of cosine of 2 theta plus 1. Okay, this is a perfectly fine way to write it. If you want to write it as 1/2 times 1 plus cosine of 2 theta, it's not required, but if you remember how we wrote sine of theta squared is 1/2 times the quantity 1 minus cosine of 2 theta. And cosine of theta squared is 1/2 times 1 plus cosine of 2 theta. Just noting the similarities in the two formulas can help you remember them. Okay, the reduction formula for tangent of theta squared. Well, we can remember that tangent of theta squared to start with is, so I'll leave that for later. So tangent of theta squared is sine of theta squared divided by cosine of theta squared. And then if we write down the reduction formula for sine of theta squared in the numerator, we get 1/2 times the quantity 1 minus cosine of 2 theta. And in the denominator, replace cosine of theta squared with 1/2 times 1 plus cosine of 2 theta. And 1/2 divided by 1/2 is 1. So our reduction formula for tangent of theta squared is 1 minus cosine of 2 theta divided by 1 plus cosine of 2 theta. So that's all there is to reducing tangent of theta squared. Okay, we'll do an exercise related to what we were just looking at. Okay, this one says simplify cosine of 9x squared minus sine of 9x squared. And then the easy way, simplify it the easy way and the hard way. I don't remember the hard way. So what does this look like? So if you remember, cosine of 2 theta is equal to cosine squared theta minus sine squared theta. So if we replace theta with 9x, then that means this will just be cosine of 2 times 9x. So cosine of 2 times 9x, or cosine of 18x, so let's test that out. I think it's pretty obvious, but if you begin with something like cosine of 18x, you can write it as cosine of 9x plus 9x. And just for practice, I'll write down the sum formula for cosine. So cosine of alpha plus beta is cosine of alpha times cosine of beta minus sine of alpha times sine of beta. And so if alpha equals beta, or if you have cosine of theta plus theta, which is cosine of 2 theta, then you get cosine of theta times cosine of theta minus sine of theta times sine of theta, which is cosine of theta squared minus sine of theta squared. So yeah, if we link those together, then cosine of 9x plus 9x is cosine of 9x squared minus sine of 9x squared. Okay, so that seems to do it. The answer is cosine of 18x. Okay, the next example, prove the identity. Sine of t minus cosine of t quantity squared equals 1 minus sine of 2t. So on this one, let's try something a little different. Let's let's do it two ways. The first way, we'll start on the left-hand side and see if we can come up with the right-hand side. And then after that, we'll begin with the right-hand side and see if we can come up with the left-hand side. So if we start with the left-hand side, sine of t minus cosine of t squared. So when we square that, we get sine of t squared minus 2 times sine of t times cosine of t plus cosine of t squared. So always be on the lookout for applying the Pythagorean identity. Sine of t squared plus cosine of t squared equals 1. So we get 1 minus 2 times sine of t times cosine of t. And then recognize an identity. 2 times sine of t times cosine of t is sine of 2t. So we ended up with the right-hand side. So that seemed to be pretty straightforward. But if we begin with the right-hand side, is it going to be as easy? 1 minus sine of 2t. Well, we can apply the formula for sine of 2t. So this is 1 minus 2 times sine of t times cosine of t. So you might see what I'm driving at here. We could just reverse the process from the first part when we started on the left-hand side. But that's using information that we wouldn't ordinarily have. So in other words, how would I know that I should replace 1 with sine of t squared plus cosine of t squared? It's not completely apparent that I would want to do that. So my point is, if we started on the right-hand side, we might come to a point where it's not obvious, not exactly obvious how to continue, but it was pretty straightforward when we started with the left-hand side. Okay, the next exercise, rewrite the sine of 8x to the 4th power with an exponent no higher than 1. Well, remember the reduction formulas. We have a reduction formula for sine of x squared and cosine of x squared. So we can rewrite sine of 8x to the 4th. We can rewrite it as sine of 8x squared times sine of 8x squared. Right, this works the way it does in regular algebra. Then we can write the reduction formula for sine of 8x squared twice and then multiply them together and see what to do after that. So the reduction formula for sine of an angle squared is 1/2 times 1 minus cosine of 2 times the angle. So 2 times 8x is 16x. So this is equivalent to sine of 8x squared, and we're multiplying it by sine of 8x squared, so we just multiply it by 1/2 times 1 minus cosine of 16x. Okay, we're not done because we have to multiply these out. 1/2 times 1/2 is 1/4. And then we'll multiply the two binomial-like quantities. 1 times 1 is 1. And we're going to subtract cosine of 16x twice. So I'll just write it as 1 minus 2 times cosine of 16x. And then plus cosine of 16x squared. Well, we still have a term with an exponent higher than 1. So now we can use a reduction formula for cosine of 16x squared. So let's rewrite what we have up to this point. So we have 1/4 times the quantity 1 minus 2 times cosine of 16x. And then we're going to use the reduction formula for cosine of 16x squared. So this is going to be plus 1/2 times 1 plus cosine of 32x. So this is an okay answer, but let's work on it a little bit. We'll work on the inside a little bit more, so we get 1 on the inside of the brackets, 1 minus 2 times cosine of 16x, and then we'll distribute multiplication by 1/2. So we get plus 1/2 plus 1/2 cosine of 32x. And lastly, we'll distribute multiplication. Well, actually, we have 1 plus 1/2. That can be, we'll do the combination all at once here. 1 plus 1/2 is 3/2. So 1/4 times 3/2 is 3/8. And then 1/4 times negative 2 cosine of 16x. So we get minus 1/2 cosine of 16x. And finally, 1/4 times 1/2 times cosine of 32x is plus 1/8 times cosine of 32x. Okay, in the next few minutes, I'm going to demonstrate how cosine of alpha minus beta formula can be thought of, or how it can be derived. Okay, so suppose we have in the unit circle suppose we have an angle alpha in standard position. So I'm not going to draw the unit circle, but just think of the endpoints as being points on the unit circle. And so the coordinates of this point are cosine of alpha and sine of alpha. And then suppose we have another angle in standard position. I'll call this beta. So this is also a point on the unit circle. So the x and y coordinates of this, so this is beta to there. So this is cosine of beta for the x coordinate and sine of beta for the y coordinate. Okay, and note the size of this angle between those two terminal sides. The size of this angle is alpha minus beta. Okay, so over here I'm going to draw another set of axes. And I'll put the alpha minus beta angle in standard position. So it would be like rotating this to the right until this side is on the x-axis. So if we do that, we'll get an angle that looks sort of like, I don't want it to be too inaccurate, but this is sort of believable. This could be our alpha minus beta in standard position. And this is a point on the unit circle, so the x-coordinate is cosine of alpha minus beta, and the y-coordinate is sine of alpha minus beta. And then also on the unit circle is the point on the x-axis where the angle is 0. So this is cosine of 0 for the x-coordinate and sine of 0 for the y-coordinate. But cosine of 0 is just 1 and sine of 0 is 0. Okay, so the idea is since this angle alpha minus beta equals this same angle alpha minus beta, it's just that this one over here is in standard position, then it should be the case that the distance from this point, the distance from that point to that point should be the same as the distance from this point to that point. Okay, so what we do is we apply the distance formula to find the distance between these 2 points, use the distance formula to find the distance between those 2 points, and the distances are equal. So remember the distance formula from basic algebra. Here we have the square root of the quantity cosine of alpha minus cosine of beta squared plus the quantity sine of alpha minus sine of beta squared. That's the distance from this point to that point. And that distance should be the same as the distance from this point to that point. So here we can write the square root of cosine of alpha minus beta minus 1 squared plus the quantity sine of alpha minus beta minus 0 squared. Okay, so we're down to 1 minute. But if you square both sides and then square the quantities, you'll eventually end up with cosine of alpha minus beta is equal to cosine of alpha times cosine of beta plus sine of alpha times sine of beta. Okay, but we're about out of time. You might try this if you have time. Simplify this equation until you end up with this result. Tomorrow we'll look at some more information from section 9.3, and then we'll also have the test to review tomorrow. That's all for today.